Alright, hello. So in this video we're looking at what are called limits at infinity. Previously we've talked about infinite limits. You might be thinking of that because you see infinity is involved somehow. And remember, an infinite limit was when we approached a number, the function value got larger and larger and larger, either positive or negative. Well, what we're looking at here is we're looking at functions where we look at limits as x increases or decreases without bounds. So the input doesn't approach a number, it just gets bigger and bigger and bigger and bigger, either positive or negative direction. And we try to see if the function gets closer and closer to some value. So even though infinity is not a number, we kind of use the same language. We say as x approaches infinity, which just means it grows without bound, or negative infinity. So here's kind of an intuitive definition. The formal definition doesn't really suit our needs, but we can make complete sense of this. So this says that suppose f is defined on some on that interval a to infinity. It just means that we get to some value, some number, where from then onward the function is defined. So we write this, and we say the limit of f of x as x approaches infinity is L. So we use the same type of language. And we say that if we can make the values of f arbitrarily close as we want to L by taking x sufficiently large. Likewise, let me say for f defined didn't include this in the typed part, but defined on negative infinity to a for some a, just like we had up here, we have the limit of f of x as x approaches negative infinity is L if the values of f can be made arbitrarily close to L by choosing large enough negative values for x. Alright, so graph interpretation, remember for an infinite limit, it said that as x is getting closer and closer to a, f is getting bigger and bigger and bigger, and our graph interpretation was a vertical asymptote. But for a limit at infinity, again, we're kind of switching the roles of x and y in some sense. You know, inputs versus outputs for where the infinity is showing up. And now if either the limit at infinity or the limit at negative infinity is L, then the graph has a horizontal asymptote and at the line y equals L. So you can kind of think of it like this. So maybe the function is doing something weird here, and then long term it starts to behave like that, where that line is the limit. So the blue is the graph of the function. It's approaching that red dotted line. That would be our horizontal asymptote. So graphically, that's kind of what's going on. So most of the limit laws that we had from previously when we were just looking at regular limits still apply. We have to be a little bit careful because sometimes infinity makes things a little complicated. So here's a reminder of those. So if both of these limits at infinity exist and are, assuming L and M are finite numbers, then if you were to add f and g, the limit would be just what you'd expect, L plus M. Likewise for differences, constant multiples, products, everything behaves nicely just like we would expect. The usual thing with the quotient, we've got to make sure we're not dividing by 0. So no change there, provided these exist. There's a couple things missing here from the earlier limit laws. Remember, one of the limits was, I think it was this. Well, basically what we've done is we've switched a with infinity or minus infinity, but we've only looked at positive infinity so far. something like this doesn't make sense anymore. So that's one of the laws that gets lost. So this one, not for limits at infinity. But the other ones that we have do make sense. So a constant, you let x get as arbitrarily large as you want, constant still is the constant. The same idea here. If we know that that is L, then you raise to the nth power, it's just going to be L to the nth power, and the same thing with the root. A little bit of a caution there about you don't want to have like a negative root, sorry, an even root of a negative number, something like that, so you got to be a little bit careful. But basically the laws and properties that we like are still working. Couple extra ones, cancellation property, squeeze through. Remember the cancellation property, that was a really useful one where if we had something like a common factor in a numerator denominator, we would cancel those and we could still compute the limit of the resulting function. Now that resulting function is a little bit different, but in terms of limits it's not different at all. And squeeze theorem, these things work as we'd expect in the limit at infinity situation. Another one is the composition. You've got that continuity condition you need, but if the limit of the inside function as x approaches infinity is b, and f is continuous at b, then the limit of f composed with g of x as x goes to infinity is f of b. And we'll make sense of this with some examples. You start getting your hands dirty, working some things out on pen and paper, and all these things will make better sense rather than just, hearing me talk math out loud. Couple extra results here. These two have to do with basically exponential functions. You can make sense of those if you just think about what those graphs look like. So that would be for both of these would be y equals a to the x, and this would be where a is greater than 1. This would be y equals a to the x, where your base a is between 0 and 1. So as you go off to infinity, that blows up. That's where you get, I'll fix this, but just for our purposes, that should be just regular infinity. So it'll look bad for the video for just a second, but when I post the notes, I'll get that changed. So sorry for that. But if a is bigger than 1 as x goes to infinity, this goes off to infinity. As x goes to negative infinity, approaches 0. And there's the second case there. But this one we use, even a little bit more. So that's a really useful one. We'll see that when we get to some examples. And here's one. So, for example, this would be the case where if you jump back where r equals 1. If r equals 1, limit as x goes to infinity of 1 over x is 0. And a rough sketch of this graph, it looks like this. So as x goes to infinity, that's going to 0. As x goes to negative infinity, this direction is going towards 0. You can think about it more analytically if you like. X gets larger and larger and larger and larger and larger, but the denominator or numerator is fixed, so you're getting a larger and larger denominator. So this whole thing must get smaller and smaller and smaller in the sense of smaller towards 0. So that's a really useful one to keep in mind. This one, if you think about, and if you haven't ever thought about this, that's okay too. But if you think about, what the graph of inverse tangent looks like. thinking of the graphs is gonna be helpful for you. That's what those limits will be. This one. Let me show you how we could do this one. So let's say 2x squared plus 1 over x squared plus 4x. And I'm going to say here, I'm assuming that x is not 0. But if I multiply by 1 over x squared over 1 over x squared, that's really multiplying by a weird looking 1, which doesn't change it. And so I end up with 2 plus 1 over x squared all over 1 plus 4 over x. And the limit as x goes to 0 of 1 over x squared is 0. The limit as x goes to 0 of 4 over x is 0. And so this is the same as that, which equals 2 over 1, which equals 2. So that's how we got to that result. And you could do this. You'll do this a lot when you're doing these types of problems. So here's the end result, and here's kind of what's floating around in the background. So again, that property that we had, really useful. A couple other notes. We also have limits at infinity, infinite limits at infinity, which is kind of crazy, maybe at first thought, but pretty common types of examples. Illustrate this isn't a big deal. So if I had something like, not worrying about a scale or anything like that, but as x gets really big, this gets really, really big, going without bounds. So not a lot we can do with that, probably not too interesting, but certainly the situation makes sense mathematically. When we do look at infinite limits at infinity, we do have to be careful because these limit laws that we have do not always apply. So for example, if you had something like this, now 3x squared, that goes to infinity, x goes to infinity, and so it would be something like infinity plus infinity. Well, this whole thing is just getting bigger and bigger and bigger, so that makes sense. We don't really have an arithmetic for infinities. We'll talk more about this down the road. But infinity plus infinity, I guess, makes sense to say it's infinity. But something like this is a little bit more problematic because this gets larger and larger and larger. This gets more and more negative. So how do they balance out? We'll talk about it down the road, but for now we don't really have the tools for it. And we don't have an arithmetic for it, and it doesn't make sense to talk about infinity minus infinity. Is it 0? Is it infinity? Is it 1? Is it minus infinity? It's not well defined. So the whole point is just that you really need to be careful with something like that. With that said, we sometimes can be clever for some of these. If I did direct sub, this might look like infinity minus infinity, but that doesn't make sense. So what I'm going to do is some manipulation first. So I'm going to multiply by x squared plus 1 plus x over x squared plus 1 plus x. In that numerator, I end up with x squared plus 1 squared, so it's just x squared plus, square root of x squared plus 1 squared, so it's x squared plus 1. Some of those middle terms cancel, minus x squared all over that. And so that ends up being this guy. And so my limit in question equals the limit as x goes to infinity of this. Now the denominator is getting larger and larger and larger. The numerator is fixed. And so this whole thing is 0. So I had to do a little bit of manipulation, but I could figure it out.